Climate-smart soil and land management. Table of content. Introduction. Chapter 1. Introduction to climate-smart agriculture. Chapter 2. Soil fundamentals and soil health. Chapter 3. Climate change and its impact on soils. Chapter 4. Principles of climate-smart soil management. Chapter 5. Conservation agriculture techniques. Chapter 6. Agroforestry and silvipastoral systems. Chapter 7. Water and irrigation management. Chapter 8. Soil amendments and nutrient management. Chapter 9. Technology and innovation in soil management. Chapter 10. Policy, institutional support, and farmer engagement. Chapter 11. Climate-smart soil management for food security. Chapter 12. Climate-smart soil management and carbon sequestration. Chapter 13. Challenges, opportunities, and future directions in climate-smart soil management. Introduction. Soil is more than just dirt beneath our feet. It is the foundation of life, the bedrock of agriculture, and a critical ally in the fight against climate change. Across the globe, soils sustain food production, store carbon, regulate water cycles, and support biodiversity. Yet, they are under unprecedented pressure from land degradation, unsustainable farming practices, and climate variability. The challenge is urgent. If soils continue to decline, global food security, livelihoods, and ecosystem stability are at risk. Climate-smart soil and land management offers a roadmap for reversing this trend. It presents strategies that are scientifically grounded, economically viable, and socially inclusive, showing how farmers, communities, and policymakers can manage soils to enhance productivity, restore fertility, and build resilience to a changing climate. This approach is not only about protecting the soil, it is about unlocking its potential to sustain life, mitigate greenhouse gas emissions, and support thriving agricultural landscapes. The book is structured to guide readers from fundamental principles to practical applications. Early chapters explore soil formation, properties, and health, providing a foundation for understanding the challenges soils face today. Subsequent chapters delve into conservation practices, agroforestry, water and nutrient management, technological innovations, and policy frameworks, illustrating how integrated approaches create resilient and productive farming systems. Case studies from around the world bring these strategies to life, demonstrating real-world success stories where climate-smart practices have transformed landscapes, livelihoods, and local economies. In an era defined by climate uncertainty, population growth, and escalating demand for food, sustainable soil management is no longer optional, it is imperative. This book bridges science, policy, and practice, offering actionable guidance for farmers, researchers, policymakers, and development practitioners who seek to protect soils while feeding the world. By implementing climate-smart strategies, we can turn soils into a solution, a tool for productivity, resilience, and a more sustainable future. So whether you are a farmer seeking practical techniques, a policymaker designing programs, or a student eager to understand the vital link between soils and climate, this book will equip you with the knowledge, tools, and inspiration to transform soils from a resource at risk into a foundation for thriving landscapes and resilient communities. Chapter 1. Introduction to Climate-Smart Agriculture. 1.1 Understanding Climate-Smart Agriculture, CSA. Climate-Smart Agriculture, CSA, is an approach that integrates climate change adaptation and mitigation into agricultural practices while ensuring food security and improving livelihoods. It is a holistic system designed to respond to the dual challenge of feeding a growing population and combating climate change. At its core, CSA seeks to increase agricultural productivity sustainably, ensuring farmers can produce more food without degrading soil or ecosystems. Enhance resilience and adaptation of crops, livestock, and farming communities to climate change impacts. Reduce or remove greenhouse gas emissions from agricultural practices. CSA is not a single technology or practice. It is a framework that combines diverse interventions across soils, water, crops, livestock, forestry, and socioeconomic systems. 1.2 The global context. Agriculture contributes significantly to global greenhouse gas (GHG) emissions, estimated at 20 to 25% of total emissions. It is also highly vulnerable to climate change. Rising temperatures affect crop yields, soil moisture, and livestock productivity. Erratic rainfall patterns lead to droughts, floods, and water scarcity. Soil degradation, erosion, and nutrient depletion reduce productivity and carbon sequestration potential. Climate-smart soil and land management practices are central to addressing these challenges. Healthy soils act as carbon sinks, retain water, improve nutrient cycling, and enhance crop resilience. 1.3 Key Principles of Climate-Smart Agriculture. CSA is guided by three interlinked pillars. Sustainably increase productivity and incomes. Ensuring that food security improves without harming the environment. Example: using improved crop varieties combined with integrated nutrient management to increase yields on smallholder farms. Adapt and build resilience to climate change. Practices that reduce vulnerability to climate risks. Example: mulching or cover cropping to reduce soil moisture loss during droughts. Reduce or remove greenhouse gas emissions. Mitigation measures in soil, crop, and livestock management. Example: agroforestry systems that sequester carbon while providing fodder and fuel wood. 1.4 Climate-smart soil and land management, the foundation. Soil and land management form the backbone of CSA. Key concepts include soil health and fertility. Healthy soils store carbon, retain water, and sustain productivity. Erosion and land degradation control. Terracing, contour farming, and reduced tillage prevent loss of fertile topsoil. Integrated nutrient and water management. Balancing fertilizers with organic amendments, conserving water through micro-irrigation and mulching. By focusing on soils, CSA enhances the resilience of entire farming systems. 1.5 Case Study 1. Conservation Agriculture in Zambia. Context: in Zambia, smallholder farmers face declining yields due to soil erosion, droughts, and nutrient depletion. Intervention: the introduction of conservation agriculture (CA) practices, including minimum tillage to reduce soil disturbance, crop rotation with legumes to enhance nitrogen content, mulching to conserve soil moisture. Outcome: maize yields increased by 20 to 30% compared to conventional tillage systems. Soil organic carbon improved, enhancing long-term soil fertility. Farmers reported reduced labor and input costs, improving profitability. This case demonstrates how CSA principles can be applied at the farm level, enhancing productivity and resilience simultaneously. 1.6 Case Study 2. Agroforestry in India. Context: in semi-arid regions of India, farmers struggle with declining soil fertility and water scarcity. Intervention: farmers adopted agroforestry systems, interplanting leguminous trees with crops. Key practices included planting nitrogen-fixing trees such as Gliricidia and Leucaena, using tree leaves as organic mulch and fodder for livestock, integrating contour planting to reduce erosion. Outcome: crop yields increased by 15 to 25% due to improved soil fertility and moisture retention. Trees sequestered -2.5 tons of carbon per hectare per year, contributing to mitigation. Livestock feed availability improved, enhancing household nutrition and income. Agroforestry illustrates a CSA approach that combines adaptation and mitigation benefits while improving livelihoods. 1.7 Benefits of climate-smart agriculture. Enhanced soil health and fertility. Improved water use efficiency. Increased productivity and income stability. Reduced vulnerability to climate shocks. Contribution to carbon sequestration and emission reduction. 1.8 Challenges in CSA implementation. Despite the benefits, challenges remain. High upfront costs of improved technologies. Lack of knowledge and extension services. Limited access to finance and markets. policy gaps, and weak institutional support. Overcoming these barriers requires integrated approaches, combining technical interventions with capacity building, policy support, and farmer engagement. 1.9 Future Outlook. Climate-smart agriculture is gaining global attention. The FAO, CGIAR, and World Bank promote CSA frameworks worldwide. Climate finance is increasingly tied to CSA practices. Advances in precision agriculture, soil sensors, and remote sensing can optimize CSA interventions. The success of CSA will depend on adapting practices to local conditions, empowering farmers, and creating policies that support sustainable soil and land management. Key takeaways. CSA addresses food security, climate adaptation, and mitigation simultaneously. Soil and land management are central to climate resilience. Conservation agriculture and agroforestry are proven CSA strategies. Implementation challenges require policy support, knowledge transfer, and finance access. Chapter 2: Soil Fundamentals and Soil Health. 2.1 Introduction. Soil is the foundation of agriculture and ecosystem health. It is a living system that supports plant growth, stores water, cycles nutrients, and sequesters carbon. Climate-smart soil management begins with understanding soil properties, processes, and the factors affecting soil health. Key objectives of this chapter. Understand soil composition and types. Explore soil fertility and nutrient cycles. Identify causes and consequences of soil degradation. Learn indicators of soil health for climate-smart interventions. 2.2 Soil formation and components. Soil formation, pedogenesis. Soil forms through physical, chemical, and biological processes, acting on parent material over time. The key factors are: parent material, rocks, sediments, and organic deposits. Climate, temperature and rainfall influence weathering and organic matter accumulation. Topography, slope and elevation affect erosion and water movement. Biota, plants, animals, and microorganisms contribute organic matter and biological activity. Time, soil formation is gradual, often taking hundreds to thousands of years. Stages of soil development. Young soils, shallow, poorly developed horizons. Mature soils, well-developed horizons, high fertility potential. Old soils, highly weathered, often nutrient-poor. Soil components. Soil consists of four main components. Mineral particles, 45%. Sand, coarse, drains quickly. Silt, medium texture, retains moisture. Clay, fine, nutrient-rich but slow drainage. Organic matter, 5%. Provides nutrients, improves soil structure, and enhances water holding capacity. Water, variable. Held in soil pores, critical for plant growth. Air, variable. Supports root respiration and microbial activity. Soil texture. Determines water retention, nutrient availability, and root penetration. Loam soils, balanced sand, silt, clay are ideal for most crops. 2.3 Soil horizons and profile. A typical soil profile has layers, horizons. O horizon, organic matter, leaf litter. A horizon, topsoil, rich in organic matter, nutrients, and microbes. B horizon, subsoil, mineral accumulation. C horizon, weathered parent material. R horizon, bedrock. Understanding horizons is critical for identifying fertility zones and soil management strategies. 2.4 Soil fertility and nutrient cycles. Major nutrients. Macronutrients, nitrogen N, phosphorus P, potassium K. Secondary nutrients, calcium Ca, magnesium Mg, sulfur S. Micronutrients, zinc Zn, iron Fe, boron B, manganese Mn, copper Cu. Nutrient cycling. Nitrogen cycle, nitrogen fixation, biological, nitrification, denitrification, and leaching. Phosphorus cycle, weathering of minerals, organic matter decomposition. Potassium cycle, mineral weathering and recycling through crop residues. Climate-smart practices enhance nutrient use efficiency by recycling organic matter, using cover crops, and reducing nutrient losses. 2.5 Soil biological properties. Healthy soils host diverse organisms. Microorganisms, bacteria, fungi, actinomycetes. Macroorganisms, earthworms, insects, and small mammals. Functions of soil organisms. Decomposition of organic matter. Nutrient mineralization and cycling. Soil aggregation and structure improvement. Disease suppression. Case study. In Kenya, integrating compost and biofertilizers in maize fields increased microbial biomass by 30 to 40%, enhancing nutrient availability and yields. 2.6 Soil degradation, causes and impacts. Causes of soil degradation. Erosion, water and wind remove topsoil. Nutrient depletion, continuous cropping without replenishment. Acidification or alkalinization, imbalanced fertilizer use or irrigation with poor quality water. Salinization, irrigation in arid areas without proper drainage. Compaction, heavy machinery or livestock pressure. Impacts of degradation. Reduced productivity and income. Lower water retention. Decreased carbon sequestration. Increased vulnerability to climate change. 2.7 Indicators of soil health. Key measurable indicators include visual and field indicators. Soil color, dark soils equals high organic matter. Soil structure, crumbly soil equals good aggregation. Root growth and earthworm count. 2.8 Climate-smart soil health practices. Conservation tillage, reduces erosion, improves organic matter. Cover crops and mulching, maintain soil moisture and nutrient cycling. Crop rotations and intercropping, reduce nutrient depletion and pest buildup. Organic amendments, compost, manure, biochar improve soil fertility. Agroforestry integration, tree roots stabilize soil and add organic matter. Case study, soil restoration in Ethiopia. Problem, degraded hillsides due to overgrazing and deforestation. Intervention, terracing, planting vetiver grass and organic amendments. Outcome, soil organic carbon increased by 15% in 5 years, crop yields improved and soil erosion reduced. 2.9 Soil monitoring and management tools. Soil testing for pH, nutrients, and organic matter. Remote sensing for erosion and land use monitoring. Farmer-friendly soil health cards to guide fertilization and amendments. Emerging innovations. Biosensors for real-time nutrient tracking. Mobile apps for soil health decision support. Key takeaways. Soil is a living dynamic system essential for agriculture and climate resilience. Healthy soils improve productivity, water retention, and carbon sequestration. Soil degradation threatens livelihoods and climate adaptation. CSA practices such as conservation tillage, cover cropping, and organic amendments restore and maintain soil health. Chapter 3, Climate Change and its Impact on Soils. 3.1 Introduction. Soils are critical for food security, water regulation, and climate mitigation. Climate change, manifested through rising temperatures, shifting precipitation patterns, and extreme weather events, directly impacts soil functions and productivity. Understanding these effects is essential for climate-smart soil and land management. Objectives of this chapter. Describe climate change impacts on soil processes. Analyze effects on soil fertility, structure, and moisture. Examine regional case studies, illustrating vulnerability and adaptation. Present strategies for building soil resilience under climate change. 3.2 Climate change drivers affecting soils. Temperature rise. Global surface temperatures have increased by -1.1 degrees Celsius since pre-industrial times, affecting soil microbial activity and organic matter decomposition. Higher temperatures accelerate mineralization of soil organic carbon, reducing carbon stocks. Soil moisture evaporation increases, exacerbating drought conditions. Altered rainfall patterns. Changes in rainfall intensity, frequency, and seasonality affect water infiltration and erosion. Heavy rainfall events increase surface runoff and soil erosion. Prolonged dry spells reduce soil moisture, affecting nutrient uptake and crop growth. Extreme weather events. Floods lead to topsoil loss and nutrient leaching. Droughts decrease microbial activity and soil fertility. Storms and hurricanes physically disrupt soil structure. 3.3 Impacts on soil physical properties. Soil moisture dynamics. Reduced water retention in sandy soils during droughts. Waterlogging in clay soils during heavy rainfall. Soil erosion. Intensified rainfall increases sheet, rill, and gully erosion. Wind erosion is exacerbated in dry, bare soils. Soil structure degradation. Loss of soil aggregation due to reduced organic matter. Compaction from flooding or machinery reduces root growth and infiltration. Case study: erosion in the Sahel region, Africa. Problem: increasing rainfall variability and deforestation lead to severe topsoil loss. Impact: soil fertility decline reduces millet and sorghum yields by 15 to 25%. Solution: agroforestry and contour bunding restored productivity and reduced erosion. 3.4 Impacts on soil chemical properties. Nutrient leaching. Heavy rainfall accelerates loss of nitrogen, potassium, and other soluble nutrients. Soil pH changes. Acidification may occur due to nitrogen fertilizer overuse and increased rainfall. Salinization. Sea level rise and improper irrigation practices increase salt accumulation in coastal soils. Case study: salinity in coastal Bangladesh. Rising sea levels and cyclones increase soil salinity in paddy fields. Adaptation strategies included salt-tolerant rice varieties and raised bed farming. 3.5 Impacts on soil biological properties. Microbial activity. Temperature and moisture fluctuations affect decomposition and nutrient cycling. Soil fauna. Earthworms and beneficial insects decline under drought or flooding stress. Carbon sequestration. Loss of organic matter reduces the soil's ability to store carbon, exacerbating greenhouse gas emissions. Case study: soil microbial response in India's semi-arid regions. Drought conditions reduce microbial biomass by up to 40%, impacting nitrogen availability. Practices like mulching and organic amendments maintained microbial activity and improved resilience. 3.6 Soil degradation and desertification. Climate change accelerates processes such as desertification, expansion of arid lands in Africa, the Middle East, and Central Asia. Land degradation, reduced productivity in already marginal lands. Loss of arable land, threatening global food security. Global example: the Loess Plateau in China underwent severe erosion. Restoration through terraces, vegetation cover, and organic amendments significantly improved soil fertility and reduced erosion. 3.7 Impacts on crop productivity. Climate-induced soil degradation affects crop yields. Case study: maize yields in sub-Saharan Africa. Maize yields declined by 10 to 20% due to soil moisture stress and nutrient loss. Conservation agriculture practices, minimum tillage, mulching, crop rotation, improved resilience and stabilized yields. 3.8 Building soil resilience under climate change. Key strategies. Conservation agriculture reduces erosion, improves organic matter, maintains moisture. Agroforestry enhances carbon storage, stabilizes soil, and provides shade. Cover cropping and mulching maintains soil moisture and reduces temperature extremes. Integrated nutrient management balances organic and inorganic fertilizers to maintain fertility. Water-smart practices, drip irrigation, rainwater harvesting, and contour bunding. Case study, climate-smart practices in Ethiopia. Hillside terraces, mulching, and cover crops reduce soil loss by 60%. Crop yields increased, and soil carbon levels improved over a 5-year period. 3.9 Monitoring and assessment tools. Soil moisture sensors for irrigation management. Remote sensing and GIS to track erosion and land degradation. Soil health indicators to assess nutrient and organic matter status. Emerging tools help farmers and policymakers make data-driven decisions to adapt soil management to changing climates. Key takeaways. Climate change directly impacts soil physical, chemical, and biological properties. Increased erosion, salinization, nutrient loss, and organic matter depletion threaten productivity. Regional case studies demonstrate the vulnerability of soils to extreme events. Climate-smart soil and land management practices enhance resilience, restore fertility, and mitigate greenhouse gas emissions. Chapter 4. Principles of Climate-Smart Soil Management. 4.1 Introduction. Climate-Smart Soil Management, CSSM, integrates soil fertility, water management, carbon sequestration, and sustainable land use to enhance productivity, resilience, and climate mitigation. It focuses on 3 core objectives. Sustainable productivity, improving yields without degrading soil. Climate resilience, adapting soils and crops to extreme weather. Mitigation of greenhouse gas emissions, sequestering carbon and reducing emissions. This chapter presents the fundamental principles, strategies, and tools for effective CSSM. 4.2 The 3 pillars of climate-smart soil management. Productivity enhancement. Integrated nutrient management, I&M, combining organic and inorganic fertilizers for balanced fertility. Crop rotation and intercropping, reduces pests, improves nutrient use efficiency, and maintains soil structure. Soil organic matter improvement, compost, green manures, and biochar enhance fertility and water retention. Case study, I&M in Vietnam's rice systems. Farmers applied compost, along with reduced chemical fertilizers. Result, rice yields increased by 15 to 20%, and nitrogen use efficiency improved by 25%, reducing environmental pollution. Resilience and adaptation. Mulching and cover crops reduce evaporation, prevent erosion, and maintain soil temperature. Water-smart practices, drip irrigation, rainwater harvesting, and contour farming. Agroforestry and mixed cropping, trees stabilize soil, provide shade, and improve nutrient cycling. Case study, contour farming in Nepal. Terraced and contour planted farms reduce soil erosion by 50 to 60%. Crop survival during erratic rainfall improved, demonstrating enhanced resilience. Mitigation and carbon sequestration. Conservation agriculture (CA), no-till or reduced-till systems increase soil carbon storage. Agroforestry systems, trees and shrubs sequester carbon above and below ground. Biochar application, stabilizes carbon in soils for decades while improving fertility. Case study, agroforestry in Kenya. Integrating leguminous trees with maize and beans increase soil carbon stocks by -2.5 tons per hectare per year. Farmers gained additional fodder and firewood, illustrating mitigation and livelihood benefits. 4.3 Soil management principles for climate-smart agriculture. Maintain soil cover. Protecting the soil with crop residues, mulches, or cover crops prevents erosion and moisture loss. Increases organic matter inputs, improving soil structure and microbial activity. Minimize soil disturbance. Reduced tillage prevents loss of soil carbon, maintains structure, and reduces erosion. No-till or strip-till systems are widely adopted in maize, wheat, and soybean systems globally. Diversify crop and land use. Rotations and intercropping reduce pest pressure and nutrient depletion. Incorporating legumes fixes nitrogen, while deep-rooted crops improve soil aeration. Optimize nutrient management. Soil testing guides precise fertilizer application. Balance nitrogen, phosphorus, potassium, and micronutrients with organic amendments. Enhances productivity while reducing emissions from over-fertilization. Enhance soil biological activity. Promote microbial diversity through compost, biofertilizers, and organic matter addition. Healthy microbial communities improve nutrient cycling, disease resistance, and carbon sequestration. 4.4 Soil water management. Rainwater harvesting captures and stores rain for irrigation during dry spells. Micro-irrigation, drip and sprinkler systems, conserves water and reduces nutrient leaching. Contour bunds and terraces, slow water runoff, reduce erosion, and increase infiltration. Case study: water harvesting in Rajasthan, India. Micro-catchments and check dams improve soil moisture availability. Crop yields increase by 25 to 30%, demonstrating effective climate-smart soil water management. 4.5 Organic amendments and soil fertility management. Compost and manure enhance nutrient content and soil structure. Green manures and cover crops fix nitrogen and protect soil. Biochar improves water retention, pH balance, and long-term carbon storage. Case study: organic amendments in Uganda. Combining compost and crop residues on degraded soils restored fertility. Maize yields increased from 1.5 t per hectare to 3 t per hectare within 3 years. 4.6 Land degradation control. Erosion control, terraces, stone bunds, and grass strips. Salinity management, proper drainage, salt-tolerant crops, and leaching techniques. Acidity correction, liming acidic soils to improve nutrient availability. Case study: Loess Plateau, China. Large-scale terraces, vegetation cover, and soil amendments restored 3 million hectares of degraded land. Soil organic carbon increased, and crop productivity doubled over a decade. 4.7 Integrating technology for CSSM. Precision agriculture, sensors, drones, and GPS-based equipment optimize fertilizer and water use. Remote sensing and GIS monitor erosion, soil moisture, and land use changes. Decision support tools guide farmers on optimal planting, fertilization, and conservation practices. Example: remote sensing in Brazil soybean fields reduced fertilizer application by 20% while maintaining yields. 4.8 Policy and institutional support. Governments and institutions can incentivize adoption of CSSM practices through subsidies for organic inputs, water-saving technologies, or biofertilizers. Extension services to train farmers. Access to climate finance and carbon markets. Case study: Ethiopia's Soil and Water Conservation Program. Provided training and support for terracing, tree planting, and composting. Result: significant reduction in erosion, improved soil fertility, and higher food security. 4.9 Key takeaways. Climate-smart soil management combines productivity, resilience, and mitigation. Core principles include maintaining soil cover, minimizing disturbance, diversifying crops, optimizing nutrients, and enhancing biology. Soil water management and organic amendments are essential for long-term soil health. Technology, policies, and farmer engagement are critical for scaling CSSM. Chapter 5: Conservation Agriculture Techniques. 5.1 Introduction. Conservation agriculture (CA) is a climate-smart farming system designed to improve soil health, water retention, and productivity while reducing greenhouse gas emissions. CA emphasizes minimal soil disturbance, reduced or no tillage, permanent soil cover, mulches and cover crops, crop diversification, rotation and intercropping. These principles restore degraded soils, improve resilience to climate variability, and sustain long-term productivity. 5.2 Principle 1: Minimal soil disturbance. Reduced and no-tillage systems. No-till. Seeds are planted directly into undisturbed soil with residues left on the surface. Reduced tillage. Soil is lightly disturbed only in planting zones, leaving most residues intact. Benefits: preserves soil structure and organic matter, reduces erosion and compaction, enhances water infiltration and retention, lowers labor and fuel costs. Case study: no-till in Argentina's Pampas. Wheat and soybean farmers adopted no-till systems over 10 million hectares. Soil organic carbon increased by -0.5% per year, and yields improved due to better moisture retention. Implementation considerations: use specialized planters for residue retention. Manage weeds through crop rotation or cover crops. Monitor soil moisture and compaction. 5.3 Principle 2. Permanent soil cover. Mulching. Covering soil with crop residues, straw, or organic materials protects against erosion and conserves moisture. Reduces soil temperature fluctuations and nutrient loss. Provides habitat for beneficial soil organisms. Case study: mulching in Kenya's maize fields. Maize residue mulch reduced evaporation by 30%, maintaining higher soil moisture during droughts. Yields increased by 15 to 20% compared to bare soil. Cover cropping. Growing legumes, grasses, or mixed species between main crops. Benefits include nitrogen fixation, organic matter addition, weed suppression, and erosion control. Example crops: legumes, clover, vetch, cowpea. Grasses, rye, sorghum, Sudan grass hybrid. Case study: cover cropping in the U.S. Midwest. Winter rye cover crops improve soil organic carbon by 0.3% annually. Reduce nitrate leaching by 20 to 25%, improving water quality. 5.4 Principle 3. Crop diversification. Crop rotation. Alternating crops improves nutrient cycling and pest disease management. Deep-rooted crops improve soil structure and reduce compaction. Example: maize right-pointing arrow, legume right-pointing arrow. Small grain rotation enhances nitrogen availability and breaks pest cycles. Case study: rotations in India's Punjab region. Farmers adopting maize pulses wheat rotations saw 25% higher yields and reduced fertilizer dependency. Intercropping. Planting 2 or more crops simultaneously on the same land. Provides soil cover, diversifies income, and enhances nutrient use efficiency. Example: maize intercropped with beans or cowpeas. Case study: intercropping in Zambia. Maize-bean intercrops increase total system yield by 20 to 30% while improving soil fertility through nitrogen fixation. 5.5 Organic matter management. Crop residues, compost, and green manures increase soil organic carbon. Improves water retention, soil structure, and microbial activity. Supports nutrient cycling and reduces dependence on synthetic fertilizers. Case study: organic amendments in Uganda. Application of compost and crop residues over 3 seasons improve topsoil organic carbon by 0.8 to 1.0%, restoring degraded soils and increasing maize yields. 5.6 Erosion control in conservation agriculture. Contour farming. Planting along natural contours reduces runoff velocity and soil loss. Terracing in bunds. Retain water and soil on slopes. Common in hilly regions prone to erosion. Case study: terracing in Ethiopia. Terraced maize fields reduce soil loss by 60%, while crop productivity increased. 5.7 Integrating livestock. Crop livestock systems recycle nutrients and organic matter. Grazing managed carefully prevents overcompaction and maintains soil cover. Manure provides organic fertilizer and improves soil fertility. Case study: silvopastoral systems in Colombia. Trees, grasses, and livestock integration improve soil organic matter and reduce soil erosion on steep slopes. 5.8 Climate benefits of conservation agriculture. Carbon sequestration. Crop residues and no-till practices store carbon in soil. Greenhouse gas mitigation. Reduced fuel use and better nitrogen management decrease emissions. Resilience to extreme events. Mulches and cover crops reduce drought and flood impacts. Example: in Brazil, adoption of CA reduced carbon dioxide emissions by -3 tons per hectare per year while increasing crop productivity. 5.9 Challenges and Solutions. 5.10 Key Takeaways. Conservation agriculture improves soil health, productivity, and resilience. Key principles: minimal soil disturbance, permanent soil cover, and crop diversification. Practices include no-till, mulching, cover cropping, rotations, and intercropping. Integrating livestock and organic amendments enhances soil fertility and carbon sequestration. CA contributes to climate mitigation while improving farmer livelihoods. Chapter 6: Agroforestry and Silvopastoral Systems. 6.1 Introduction. Agroforestry and silvopastoral systems are climate-smart approaches that combine trees, crops, and livestock in the same landscape. These systems provide multiple benefits: improve soil health and fertility, enhance water retention and reduce erosion, increase carbon sequestration, diversify farmer income and food sources, support resilience to climate variability. By integrating woody perennials with crops and livestock, these systems mimic natural ecosystems while sustaining agricultural productivity. 6.2 Agroforestry Systems. Definition and Types. Agroforestry is the deliberate integration of trees and shrubs into crop and livestock systems. Common types include alley cropping. Trees planted in rows with crops grown in between. Example trees: Leucaena, Gliricidia, Suspania. Benefits: nitrogen fixation, organic matter input, shade regulation. Boundary and fodder planting. Trees or shrubs planted along field boundaries for fodder, fuelwood, or windbreaks. Silvopastoral systems. Combines trees, grasses, and livestock grazing. Provides shade, fodder, and improved soil structure. Home gardens and multistrata systems. Diverse plantings around homesteads, combining fruits, vegetables, and medicinal plants. Soil and water benefits of agroforestry. Soil fertility enhancement. Leguminous trees fix nitrogen and add organic matter through leaf litter and pruning residues. Erosion control. Tree roots stabilize soil, reduce runoff, and protect against wind erosion. Improved water retention. Leaf litter and mulch increase infiltration and moisture retention. Case study: alley cropping in Malawi. Farmers planted Faidherbia albida between maize fields. Soil nitrogen increased by 25 to 30 kilograms per hectare per year, and maize yields improved by 20 to 35%. Carbon sequestration. Trees sequester carbon both above ground, wood and leaves, and below ground, roots and soil organic matter. Agroforestry systems can store 2 to 6 tons of carbon per hectare per year, depending on species and management. Example: in Kenya, smallholder farms with Gliricidia and Napier grass sequestered -3 tons C per hectare per year, while producing fodder and firewood. Biodiversity and ecosystem services. Provides habitats for pollinators and beneficial insects. Reduces pest pressure in adjacent crops. Enhances resilience against climate extremes. 6.3 Silvopastoral Systems. Definition. Silvopastoral systems integrate trees, forage plants, and livestock grazing on the same land. They are especially suitable for semi-arid and hilly regions. Benefits. Shade and shelter, protects livestock from heat stress. Soil fertility, manure combined with leaf litter enriches soils. Erosion control, tree roots prevent runoff, especially on slopes. Income diversification, provides timber, fodder, fruits, and firewood. Case study: silvopastoral systems in Colombia. Farmers planted trees like Inga edulis among pastures. Soil organic matter increased by 1 to 2% over 5 years. Livestock weight gains improved by 10 to 15% due to shade and quality fodder. 6.4 Designing agroforestry and silvipastoral systems. Site selection. Soil type, slope, rainfall, and climate determine suitable species. Avoid waterlogging or highly acidic soils unless managed appropriately. Species selection. Nitrogen-fixing trees, Leucaena, Gliricidia, Acacia. Fruit trees, mango, guava, citrus. Fodder trees, Calliandra, Suspania. Timber species, teak, eucalyptus with caution for water use. Spatial arrangement. Trees in rows, alley cropping, or scattered parkland system. Livestock grazing areas, rotated to prevent overgrazing. Mulching and residue management to protect soil. 6.5 Agroforestry for climate resilience. Drought mitigation. Deep-rooted trees access water unavailable to crops. Flood mitigation. Trees reduce runoff and improve infiltration. Heat stress reduction. Shade protects crops, livestock, and soil. Example, in India's semi-arid regions, Faidherbia albida-based agroforestry increased maize yields during dry seasons by 30 to 40%. 6.6 Economic and livelihood benefits. Diversified products, timber, fruit, fodder, fuelwood, medicinal plants. Reduced risk from crop failure due to diversified income streams. Increased resilience of smallholder farmers to climate shocks. Case study, agroforestry in Nepal. Integrating fodder trees with maize and vegetables provided additional income of $300 minus $400 per hectare per year. Soil erosion decreased, and soil fertility improved over 5 years. 6.7 Challenges and solutions. 6.8 Key takeaways. Agroforestry and silvopastoral systems enhance soil health, water retention, and carbon sequestration. They provide climate resilience by mitigating drought, floods, and heat stress. Integration of trees, crops, and livestock increases farmer income and ecosystem services. Successful implementation requires careful species selection, spatial arrangement, and community support. Chapter 7. Water and Irrigation Management. 7.1 Introduction. Water is a critical resource in agriculture. Climate change, through droughts, floods, and erratic rainfall, poses serious challenges to water availability. Efficient soil water management is therefore a cornerstone of climate-smart agriculture, CSA. Proper water management maintains soil moisture for crop growth, prevents erosion and nutrient loss, enhances soil carbon sequestration, improves resilience to climate variability. This chapter presents strategies, technologies, and case studies for efficient water use in soil and land management. 7.2 Soil-water relationships. Soil-water holding capacity. Field capacity. Maximum water soil can retain after excess drains. Permanent wilting point. Moisture level below which plants cannot extract water. Available water capacity. Difference between field capacity and wilting point. Critical for crop planting. Example, sandy soils have low water holding capacity, while clay soils retain water but may cause waterlogging. Soil texture and structure effects. Sandy soils, fast drainage, low nutrient retention. Clay soils, high water retention, slow infiltration. Loam soils, balanced drainage and retention, ideal for most crops. Improving soil organic matter through compost or mulching increases water retention across all soil types. 7.3 Efficient irrigation systems. Surface irrigation. Traditional methods, furrows, basins, and flooding. Pros, simple, low capital. Cons, high water loss through evaporation and runoff. Micro irrigation. Drip irrigation, delivers water directly to plant roots. Sprinkler irrigation, distributes water uniformly over the field. Benefits of micro-irrigation. Water savings of 30 to 60% compared to surface irrigation. Reduced nutrient leaching. Improved crop yields and quality. Case study, drip irrigation in Israel. Citrus orchards using drip systems increased yields by 20 to 40% while reducing water use by 50%. Subsurface irrigation. Water is delivered below the soil surface through buried pipes. Reduces evaporation losses and improves root zone moisture availability. 7.4 Rainwater harvesting. Captures and stores rainfall for agricultural use. Techniques include ponds, tanks, check dams, and contour bunds. Benefits. Reduces dependence on groundwater. Prevents soil erosion. Improves resilience during drought. Case study: check dams in Rajasthan, India. Restored groundwater levels. Enabled multiple cropping cycles in previously rain-fed areas. Improved soil moisture and crop yields by 25 to 30%. 7.5 Soil and water conservation techniques. Mulching. Reduces evaporation and moderates soil temperature. Enhances organic matter and microbial activity. Contour bunding and terracing. Slows water runoff, reduces erosion. Increases infiltration and soil moisture. Cover cropping. Protects soil surface, reduces compaction, and improves infiltration. Leguminous cover crops add nitrogen and organic matter. 7.6 Integrated soil water management. Combines soil amendments, irrigation, and conservation practices for optimal water use. Practices include organic matter addition for moisture retention, minimum tillage to reduce evaporation, efficient irrigation scheduling based on crop needs. Case study: integrated management in Ethiopia. Terracing, mulching, and drip irrigation increase maize yields by 40% under erratic rainfall conditions. Soil organic carbon improved by 0.5 to 1.0% over 5 years. 7.7 Climate smart irrigation strategies. Deficit irrigation. Apply water below full crop requirements to optimize water use efficiency. Alternate wetting and drying, AWD, particularly for rice cultivation to save water and reduce methane emissions. Sensor-based irrigation. Soil moisture sensors guide irrigation scheduling. Smart scheduling. Align irrigation with weather forecasts and crop phenology. Example: AWD in rice systems in the Philippines reduce water use by 25 to 30% while maintaining yields. 7.8 Challenges in water management. 7.9 Policy and institutional support. Subsidies for micro-irrigation systems. Promotion of water user associations. Incentives for rainwater harvesting and watershed management. Integration of CSA water management into national agricultural policies. Case study: Israel's water policy for agriculture. Supported widespread adoption of drip irrigation. Enabled high productivity with minimal water use. Serves as a model for arid and semi-arid regions worldwide. 7.10 Key takeaways. Soil water management is central to climate-smart agriculture. Efficient irrigation, rainwater harvesting, and conservation practices enhance productivity and resilience. Integrating organic amendments and cover crops improves soil water retention. Technology, policy support, and farmer engagement are critical for scaling climate-smart water management. Chapter 8: Soil Amendments and Nutrient Management. 8.1 Introduction. Soil fertility is a critical determinant of agricultural productivity. Climate-smart soil management emphasizes enhancing soil fertility while minimizing environmental impact. Nutrient management strategies involve balancing organic and inorganic amendments, maintaining soil biological activity, and preventing nutrient losses. This chapter covers types of soil amendments, integrated nutrient management, I&M, biofertilizers, and microbial interventions, soil testing and nutrient optimization. Case studies demonstrating climate-smart nutrient management. 8.2 Types of soil amendments. Organic amendments. Organic amendments improve soil structure, Water retention and microbial activity. Common options include compost. Decomposed organic matter from crop residues, manure, or kitchen waste. Adds nutrients slowly, improving fertility over time. Manure. Livestock manure provides nitrogen, phosphorus, potassium, and organic matter. Enhances microbial biomass and soil aggregation. Green manure. Incorporation of nitrogen-fixing crops, e.g. legumes, into the soil. Supplies nitrogen and organic matter. Biochar. Charred organic material applied to soil. Improves water retention, nutrient retention, and long-term carbon storage. Case study: biochar application in Uganda. Maize fields receiving biochar combined with compost increased yields by 20 to 25%. Soil organic carbon increased, improving fertility and drought resilience. Inorganic fertilizers. Supply essential macro and micronutrients, NPK, Ca, Mg, Sen, Fe, B, Mn, Cu. Rapidly addresses nutrient deficiencies. Overuse can lead to soil acidification, nutrient leaching, and greenhouse gas emissions. Climate-smart practice. Use precise, site-specific fertilizer applications guided by soil testing to avoid over-application and reduce environmental impact. 8.3 Integrated Nutrient Management, INM. INM combines organic and inorganic fertilizers for sustainable nutrient supply. Key principles. Apply organic amendments to improve soil structure and biological activity. Use chemical fertilizers to meet crop nutrient demands efficiently. Monitor soil fertility using soil testing and plant tissue analysis. Include legumes and cover crops to naturally fix nitrogen. Benefits. Maintains or improves soil fertility. Enhances crop yields and nutrient use efficiency. Reduces GHG emissions from fertilizers. Case study: INM in Vietnam rice systems. Farmers combined compost with reduced synthetic fertilizer. Yield increased by 15 to 20%, and nitrogen use efficiency improved by 25%, reducing environmental pollution. 8.4 Microbial and biofertilizer interventions. Biofertilizers contain living microorganisms that promote nutrient availability. Common types: nitrogen-fixing bacteria, Rhizobium azotobacter. Phosphate-solubilizing bacteria, PSB. Mycorrhizal fungi for phosphorus uptake. Benefits: reduce dependency on chemical fertilizers. Improve soil health and microbial diversity. Enhance resilience under climate stress. Case study: Rhizobium inoculation in Kenya. Soybean crops inoculated with Rhizobium increase nitrogen fixation by 50 to 60 kilograms per hectare. Improved yields and soil fertility while reducing fertilizer costs. 8.5 Soil pH and liming. Soil pH affects nutrient availability. Acidic soils limit phosphorus and molybdenum availability. Alkaline soils reduce availability of iron, zinc, and manganese. Liming acidic soils neutralizes pH, improves fertility, and increases microbial activity. Sulfur amendments can acidify alkaline soils when needed. Example: liming acidic soils in Ethiopia increased maize yields by 15 to 20% over 3 years. 8.6 Nutrient Management Planning. Soil testing. Determines nutrient deficiencies and guides fertilizer application. Fertilizer recommendation. Based on crop type, soil fertility, and expected yield. Timing and placement. Split application reduces nutrient loss. Placement near root zone improves efficiency. Monitoring and adjustment. Leaf and soil analysis guide adaptive nutrient management. 8.7 Climate-smart nutrient management practices. Use of slow-release fertilizers to reduce leaching and nitrous oxide emissions. Incorporation of crop residues to recycle nutrients. Combined use of organic and inorganic inputs to balance fertility and reduce emissions. Use of leguminous cover crops for biological nitrogen fixation. Case study: integrated nutrient management in India. Maize-wheat rotations using compost plus synthetic fertilizer plus legume cover crops improved yields by 20 to 30%. Nitrogen use efficiency increased, and soil organic carbon levels rose. 8.8 Challenges and Solutions. 8.9 Key Takeaways. Soil amendments enhance fertility, structure, water retention, and microbial activity. I&M balances organic and inorganic inputs for sustainable productivity. Biofertilizers and microbial interventions reduce chemical fertilizer dependence. Soil pH management ensures nutrient availability. Climate-smart nutrient management improves yields while mitigating environmental impacts. Chapter 9. Technology and Innovation in Soil Management. 9.1 Introduction. Modern technology plays a crucial role in enhancing soil management, improving productivity, and supporting climate-smart agriculture (CSA). Innovations range from precision agriculture tools to remote sensing and decision support systems, enabling farmers and policymakers to make informed decisions about soil health, nutrient management, water use, and erosion control. This chapter explores precision agriculture and soil sensors, remote sensing and GIS applications, decision support tools and mobile apps, innovations in soil monitoring and carbon management. Case studies demonstrating technology adoption. 9.2 Precision agriculture for soil management. Definition. Precision agriculture (PA) involves managing spatial and temporal variability in soils and crops to optimize inputs and maximize efficiency. Key technologies. GPS, guided machinery. Tractors and planters equipped with GPS for accurate sowing, fertilization, and tillage. Variable rate technology, VRT. Adjusts fertilizer, water, or pesticide application according to soil and crop needs. Soil sensors. Measure moisture, nutrient levels, pH, and temperature in real time. Drones and UAVs. Monitor soil erosion, crop growth, and stress conditions. Benefits. Reduces input costs and environmental pollution. Improves water use efficiency and nutrient management. Enhances crop productivity and soil health. Case study: precision fertilizer application in the U.S. Corn Belt. Variable rate nitrogen application reduced fertilizer use by 15 to 25% while maintaining yields. Nitrous oxide emissions were reduced, contributing to climate mitigation. 9.3 Remote sensing and GIS applications. Remote sensing uses satellite imagery or drones to assess soil moisture and texture, erosion and degradation, vegetation cover, and crop health. Example: Sentinel-2 imagery helps monitor soil organic carbon changes over large areas. Geographic Information Systems, GIS. Integrates soil, topography, land use, and climate data. Enables mapping of soil fertility zones, erosion-prone areas, irrigation potential. Case study: soil fertility mapping in Kenya. GIS-based soil maps guided fertilizer recommendations for smallholder farms. Result: optimized fertilizer use, improved yields, and reduced nutrient runoff. 9.4 Soil moisture and nutrient sensors. Soil moisture sensors measure volumetric water content and guide irrigation scheduling. Nutrient sensors detect soil nitrate, phosphorus, and potassium in real time. Automated data logging and cloud integration allow remote monitoring and decision-making. Example: drip-irrigated tomato fields in Israel use soil moisture sensors to reduce water use by 40% while maintaining crop quality. 9.5 Decision support systems, DSS, and mobile apps. Decision support systems integrate soil, weather, and crop data to provide recommendations. Mobile apps provide farmers with fertilizer and irrigation schedules, pest and disease alerts, soil health tracking. Example: Climate Smart Agriculture DSS in India. Smallholder farmers received SMS-based alerts for irrigation and fertilization. Improved water use efficiency and optimized nutrient application, increasing productivity by 15 to 20%. 9.6 Soil carbon and greenhouse gas monitoring. Technologies measure carbon sequestration and greenhouse gas emissions from soils. Eddy covariance systems for carbon dioxide flux monitoring. Soil carbon analyzers for lab and field use. Remote sensing and modeling for large-scale soil carbon assessments. Case study: soil carbon monitoring in Brazil. No-till and agroforestry systems were monitored using remote sensing and field sensors. Soil carbon sequestration increased by -2–3 tc per hectare per year, supporting carbon credit programs. 9.7 Innovations in climate-smart soil management. Biosensors and nanosensors detect soil nutrient levels and stress factors at high precision. Automated irrigation systems combine soil moisture sensors with AI for optimal water delivery. Machine learning and AI predict soil erosion risk, crop nutrient requirements, and climate impacts. Digital soil mapping combines big data, remote sensing, and GIS for high-resolution soil fertility maps. Example: AI models in India predict areas at risk of soil erosion, guiding targeted conservation interventions. 9.8 Challenges in technology adoption. 9.9 Key takeaways. Technology enhances precision, efficiency, and climate resilience in soil management. Tools such as soil sensors, drones, GIS, and decision support systems improve fertility management, irrigation, and erosion control. Soil carbon monitoring supports mitigation and carbon credit opportunities. Adoption requires training, cost support, and integration with local knowledge. Future innovations, including AI, nanosensors, and big data, will further advance climate-smart soil and land management. Chapter 10. Policy, Institutional Support, and Farmer Engagement. 10.1 Introduction. Sustainable soil and land management requires more than technical interventions. It depends on supportive policies, strong institutions, and active farmer engagement. Climate-smart soil management, CSSM, is most effective when enabling environments guide adoption, scaling, and monitoring. This chapter explores policy frameworks for climate-smart agriculture, institutional roles and capacity building, farmer engagement and participatory approaches, incentives, subsidies, and financing mechanisms, case studies of successful policy-driven initiatives. 10.2 Policy frameworks for climate-smart soil management. National agricultural policies. Policies promoting sustainable land use, soil fertility, and climate adaptation are critical. Integration of CSSM into national frameworks includes soil health programs, water conservation schemes, agroforestry, and terrace development policies, subsidies for organic inputs, biofertilizers, and microirrigation. Example: India's Soil Health Card Scheme provides farmers with detailed soil nutrient information, guides fertilizer application, and reduces overuse. Improved nutrient use efficiency and yields. Climate change policies. Policies linking soil management to mitigation and adaptation. Carbon sequestration initiatives, REDD+ programs. Climate-smart agriculture promotion in national adaptation plans. Emission reduction strategies through conservation agriculture. Example: Ethiopia's climate-resilient green economy strategy. Prioritize soil and water conservation, agroforestry, and organic amendments. Reduce land degradation, and improve smallholder productivity. 10.3 Institutional roles. Government agencies. Ministries of Agriculture, Environment and Water coordinate CSSM programs. Responsibilities: policy enforcement, extension services, subsidies, and monitoring. Research and extension institutions. Conduct research on soil health, erosion control, and nutrient management. Provide technical support and knowledge transfer to farmers. Promote innovations like biofertilizers, drip irrigation, and soil sensors. NGOs and community-based organizations. Facilitate farmer training and participatory approaches. Support microfinance, cooperatives, and resource pooling. Promote adoption of climate-smart practices. Case study: soil and water conservation in Nepal. Community forestry groups implemented terracing, contour bunding, and agroforestry. Reduced erosion, restored fertility, and enhanced livelihoods. 10.4 Farmer engagement and participatory approaches. Active farmer participation ensures ownership, adoption, and sustainability. Approaches include farmer field schools, FFS, practical learning on soil health, water management, and agroforestry. Demonstration plots, showcasing conservation agriculture, composting, or terrace systems. Participatory research, farmers co-develop techniques with researchers. Peer learning networks, farmers exchange knowledge and innovations. Example: farmer field schools in Kenya. Farmers trained in composting, mulching, and cover cropping. Adoption increased by 70%, improving yields and soil resilience. 10.5 Incentives and financing mechanisms. Subsidies reduce cost of organic inputs, microirrigation, and biofertilizers. Credit access, microfinance for smallholders to invest in soil and water management. Payment for ecosystem services, PES, rewards farmers for carbon sequestration or erosion control. Insurance schemes protect against climate-induced crop losses. Case study: PES for soil carbon in Colombia. Farmers received payments for maintaining agroforestry systems. Encouraged adoption of climate-smart practices while improving soil carbon stocks. 10.6 Community-based soil and land management. Watershed management committees oversee soil conservation, water harvesting, and afforestation. Cooperative input supply chains ensure affordable access to fertilizers, biochar, and seeds. Local monitoring networks track soil health, erosion, and carbon sequestration. Example: Community Watershed Program in India. Implemented check dams, contour bunds, and tree planting. Restored degraded lands, improved groundwater recharge, and increased agricultural productivity. 10.7 Monitoring and evaluation. Policies and programs require continuous assessment to track adoption, productivity, and environmental impact. Tools include soil health monitoring, remote sensing and GIS for land use and erosion tracking, farmer surveys and participatory assessments. Example: soil health card monitoring in India improved fertilizer application practices nationwide within 5 years. 10.8 Challenges in policy and institutional support. 10.9 Key takeaways. Policies, institutions, and incentives enable adoption of climate-smart soil practices. Farmer engagement through participatory approaches ensures ownership and sustainability. Monitoring, extension, and research support are critical for scaling impact. Financial mechanisms, subsidies, and PES schemes encourage long-term soil health investments. Integrating soil management into national climate and agricultural strategies strengthens resilience, productivity, and mitigation. Chapter 11. Climate-smart soil management for food security. 11.1 Introduction. Food security depends directly on soil health and productivity. Degraded soils, nutrient depletion, and climate variability threaten the ability of smallholder and commercial farmers to meet growing food demand. Climate-smart soil management CSSM ensures that soil remains fertile, productive, and resilient under changing climate conditions. This chapter explores the role of soils in crop productivity and food systems, soil management strategies that enhance food security, case studies linking soil health with yields and nutrition, challenges and solutions for scaling up climate-smart practices. 11.2 The link between soil health and food security. Healthy soils provide nutrients, water, and structural support for crops. Soil degradation reduces productivity, increases vulnerability to droughts and floods, and threatens food availability. Climate-smart soil management improves yield stability under climate stress, nutrient content of crops, resilience of smallholder farming systems. Example: maize yields in sub-Saharan Africa declined by 15 to 20% due to poor soil fertility and erratic rainfall. Adoption of conservation agriculture and organic amendments restored productivity. 11.3 Strategies linking soil management to food security. Soil fertility management. Integrated nutrient management, INM, ensures balanced supply of nutrients. Organic amendments, compost, manure, biochar, improve fertility, water retention, and microbial activity. Case study: rice-wheat system in India. Applying compost and chemical fertilizers increased rice and wheat yields by 20 to 25%. Improved nutrient use efficiency and soil health. Conservation agriculture. Minimal soil disturbance, cover cropping, and crop rotations protect soil, reduce erosion, and enhance productivity. Supports long-term sustainability of food systems by maintaining soil quality. Case study: maize production in Zambia. Farmers using CA achieved 20 to 30% higher yields during drought years. Soil moisture retention improved resilience to climate shocks. Agroforestry and silvopastoral systems. Trees improve nutrient cycling, increase carbon sequestration, and provide fodder and fruits. Diversifies farm income, reducing vulnerability to crop failures. Case study: agroforestry in Kenya. Maize legume tree systems increased total farm productivity by 30%. Enhanced smallholder food security and nutrition. Water-smart soil management. Efficient irrigation, rainwater harvesting, mulching, and soil amendments maintain moisture availability. Ensures crop survival during drought and erratic rainfall. Case study: drip irrigation in Israel. Citrus and vegetable yields increased by 20 to 40% with reduced water use. Soil health improved due to targeted water delivery and reduced nutrient leaching. Climate-resilient crop varieties. Integration of drought and heat-tolerant varieties with healthy soils enhances yield stability. Soil fertility and moisture management optimize the performance of resilient varieties. Example: drought-tolerant maize in Ethiopia produced 25% higher yields under low rainfall when combined with mulching and compost application. 11.4 Nutrient management for food quality. Healthy soils improve micronutrient content of crops, iron, zinc, vitamin A. Biofortification, combined with organic soil amendments, ensures nutrient-dense food production. Case study: zinc-enriched wheat in India. Applying zinc fertilizers with compost increased grain zinc concentration by 15 to 20%. Enhanced nutritional value while maintaining soil fertility. 11.5 Scaling up climate-smart soil practices. Adoption requires farmer training, extension support, and enabling policies. Community-based approaches, cooperatives, and farmer field schools facilitate widespread uptake. Technology, monitoring, and decision support tools guide implementation at scale. Example: Soil Health Card and FFS programs in India scaled up nutrient management practices to millions of farmers, improving food security and soil fertility. 11.6 Challenges and solutions. 11.7 Policy and institutional support. Policies linking soil management to food security. subsidies for organic inputs and water-saving technologies, carbon and ecosystem service incentives, research and extension support, institutions, ministries, research centers, NGOs, cooperatives. Example: Ethiopia's climate-resilient green economy integrates soil conservation, agroforestry, and water-smart agriculture to enhance national food security. 11.8 Key takeaways. Healthy soils are foundational to food security. Climate-smart soil practices enhance yield stability, nutrition, and resilience. Integrated strategies, nutrient management, conservation agriculture, agroforestry, and water-smart management maximize food production sustainably. Scaling adoption requires policy support, farmer engagement, and institutional capacity. Linking soil health to nutrition and climate resilience ensures long-term food security under changing climate conditions. Chapter 12: Climate-Smart Soil Management and Carbon Sequestration. 12.1 Introduction. Soils play a critical role in the global carbon cycle, storing more carbon than the atmosphere and vegetation combined. Climate-smart soil management, CSSM, enhances carbon sequestration while improving soil fertility, water retention, and productivity. Key objectives of this chapter: understanding soil carbon dynamics, climate-smart practices for carbon sequestration, quantifying soil carbon and greenhouse gas mitigation, case studies demonstrating CSSM for climate mitigation. 12.2 Soil carbon dynamics. Forms of soil carbon. Organic carbon, SOC, derived from plant residues, roots, and microbial biomass. Inorganic carbon, SIC, found in calcareous soils as carbonates. SOC is the primary target for CSSM practices, influencing soil structure, fertility, and water holding capacity. Carbon pools in soil. Active pool, fast-cycling organic matter readily decomposed. Slow pool, stabilized organic matter, contributes to long-term fertility. Passive pool, resistant organic matter, sequesters carbon for decades to centuries. 12.3 Climate-smart practices for carbon sequestration. Conservation agriculture. No-till reduced tillage, reduces society loss through oxidation. Residue retention, adds carbon to the soil. Crop rotations, diversified residues enhance society accumulation. Case study, no-till maize in Brazil. SOC increased by 0.3 to 0.5 Tc per hectare per year. Reduced carbon dioxide emissions from tillage operations. Agroforestry systems. Trees contribute above-ground and below-ground carbon stocks. Leaf litter and pruning residues enhance SOC. Diversifies income and enhances resilience. Example: smallholder farms in Kenya integrating Gliricidia with maize increase soil carbon by -2.5 Tc per hectare per year. Organic amendments. Compost, manure, and biochar improve society and soil fertility. Biochar is particularly effective for long-term carbon stabilization. Enhances water retention and microbial activity. Case study, biochar in Uganda. Addition of biochar increased SOC by 0.8 to 1.2% in degraded soils. Improved maize yields and drought resilience. Cover crops and green manures. Incorporation of legumes and grasses contributes biomass to the soil. Improves nitrogen availability and carbon sequestration. Protects soil from erosion. Example: winter rye cover crops in the U.S. Midwest increased SOC by 0.3% over 5 years while reducing nitrate leaching. 12.4 Soil carbon monitoring and quantification. Soil sampling and laboratory analysis measures society concentrations and stocks. Remote sensing and GIS maps soil carbon changes over large areas. Modeling approaches predict society changes under different management scenarios, e.g., Roth-C century models. Example: Roth-C modeling in China's lowest plateau predicted society gains of 0.5 to 1 Tc per hectare per year under terracing and mulching practices. 12.5 Greenhouse gas mitigation. CSSM reduces emissions of carbon dioxide, N2O, and carbon tetrahydride through reduced tillage and residue retention. Optimized fertilizer application, I&M. Agroforestry and silvopastoral integration. Water management in rice paddies, alternate wetting and drying. Case study, AWD rice in the Philippines. Methane emissions reduced by 25 to 30% while maintaining yields. Soil carbon levels remain stable or increased. 12.6 Policy and incentive mechanisms. Carbon credits and PES schemes reward farmers for sequestration practices. National climate policies support soil carbon initiatives. Extension services promote CSSM adoption to achieve mitigation goals. Example, Colombia's PES program incentivized agroforestry adoption, increasing soil carbon while improving livelihoods. 12.7 Challenges and solutions. 12.8 Key takeaways. Soils are a major carbon sink with potential to mitigate climate change. Climate-smart practices such as conservation agriculture, agroforestry, biochar, and cover crops enhance society and reduce emissions. Monitoring and modeling are essential for quantifying carbon sequestration and supporting carbon markets. Policies and incentives accelerate adoption of carbon-friendly soil management. Integrating carbon sequestration with soil fertility, productivity, and resilience ensures co-benefits for food security and climate adaptation. Chapter 13. Challenges, Opportunities, and Future Directions in Climate-Smart Soil Management. 13.1 Introduction. Climate-smart soil management, CSSM, is essential for sustainable agriculture, food security, and climate change mitigation. Despite proven benefits, adoption faces challenges ranging from technical barriers to institutional and socioeconomic constraints. This chapter examines these challenges, highlights emerging opportunities, and explores future directions for scaling climate-smart practices globally. 13.2 Key challenges in CSSM. Soil degradation. Soil erosion, compaction, salinization, and nutrient depletion remain widespread. Degraded soils limit crop productivity and resilience. Climate change exacerbates soil loss through extreme rainfall, droughts, and flooding. Example, Sub-Saharan Africa loses -30 to 40 tons of soil per hectare per year, threatening food production. Knowledge and capacity gaps. Limited farmer awareness of CSSM techniques. Inadequate extension services and technical training. Low adoption of innovations like soil sensors, biofertilizers, and precision agriculture. Economic and financial constraints. High upfront costs for irrigation systems, mechanization, or soil amendments. Limited access to credit or subsidies for smallholder farmers. Uncertainty about short-term economic returns reduces adoption. Policy and institutional barriers. Fragmented agricultural and environmental policies. Weak enforcement of soil conservation regulations. Limited coordination among government, research institutions, and NGOs. Climate variability. Droughts, floods, and unpredictable rainfall patterns challenge soil and crop management. Resilience depends on integrating water management, soil fertility, and agroforestry strategies. 13.3 Opportunities in Climate-Smart Soil Management. Technological innovations. Precision agriculture, sensors, drones, and remote sensing enhance soil monitoring and decision-making. AI and machine learning predict soil degradation and optimize management. Biochar, compost, and biofertilizers improve fertility and carbon sequestration. Policy and financial instruments. Subsidies, carbon credits, PES schemes, and insurance programs encourage adoption. Government and NGO programs can scale soil restoration and conservation practices. Example: Colombia's PES program rewards farmers for maintaining soil carbon through agroforestry. Farmer-led and community-based approaches. Farmer field schools, FFS, cooperatives, and participatory research improve knowledge transfer and adoption. Community watershed management enhances soil and water conservation on a landscape scale. Climate-smart practices with co-benefits. Conservation agriculture, cover crops, and agroforestry improve soil fertility and water retention, carbon sequestration, biodiversity, and ecosystem services. Resilience to climate shocks. 13.4 Future directions. Integration of technology and traditional knowledge. Combine modern precision tools with indigenous soil management practices. Example: contour farming and mulching guided by soil sensors. Scaling climate-smart practices. Encourage regional cooperation, knowledge networks, and policy alignment. Integrate CSSM into national climate adaptation and food security strategies. Research and innovation. Focus on soil carbon dynamics, microbial interventions, and nutrient cycling. Develop cost-effective and locally adapted technologies. Promote multidisciplinary research linking soil science, climatology, and socioeconomics. Climate finance and incentives. Access to international climate funds for soil carbon sequestration, agroforestry, and conservation agriculture. Develop market-based approaches for ecosystem services. Education and capacity building. Expand farmer training programs, extension services, and e-learning platforms. Empower youth and women in soil management and climate-smart agriculture. 13.5 Synthesis of lessons learned. Soil health is foundational to productivity, food security, and climate resilience. CSSM practices, conservation agriculture, agroforestry, integrated nutrient management, and water-smart interventions provide multiple ecological and socioeconomic benefits. Technology and innovation enhance efficiency and monitoring, but adoption requires training and incentives. Policy, institutions, and community engagement are critical for scaling and sustainability. Carbon sequestration and mitigation co-benefits highlight the global importance of soil management. 13.6 Key recommendations. Promote integrated soil, water, and nutrient management for climate resilience. Enhance technology access and adoption, including precision agriculture and remote sensing. Strengthen policy frameworks and institutional support. Encourage participatory approaches to empower farmers and communities. Invest in research and monitoring to measure impacts on soil health, productivity, and carbon sequestration. 13.7 Conclusion. Climate-smart soil management is essential for sustainable agriculture, food security, and climate change mitigation. While challenges remain, soil degradation, financial barriers, and knowledge gaps, the opportunities are immense. By combining traditional practices, technological innovations, sound policies, and community engagement, CSSM can transform agricultural landscapes into productive, resilient, and climate-smart systems.